Today we're going to see a new type of learning, reinforcement learning, and deep reinforcement learning. I'm going to start this first lecture before the break with the basics on reinforcement learning, so a brief introduction, and this notion of Markov decision processes, what are policies, how we can evaluate them, and how we can improve them. But this still in a more abstract approach. We are not yet considering deep reinforcement learning and the role of deep neural networks. On the second lecture today, we'll start looking at how to use deep neural networks for this, and then I'll present the second assignment, which will be on this topic. So the idea here is that in supervised learning that we saw so far, we have some targets that we want to predict, and so we can evaluate the performance of our models and improve the performance with gradient descent, like we saw, in order to minimize the error to that target. We also saw this context of unsupervised learning, which from the perspective of the network, it's still the same thing. There is a target. We want to optimize the network by feeding it to that target. But from our perspective, it's unsupervised because we don't need to label things. Things like autoencoders, for example, work in this way. In reinforcement learning, we will see that the role of the deep neural network is still the same. We need to have some target value and optimize the network in the same way. But we have a different situation here. So we have an agent that can perform actions, and these actions will affect the state of the environment. Furthermore, the agent has access to the environment through some interpreter. It can be a set of sensors, things like that, that can tell the agent what the agent sees about the state, this observation, and also some reward or some indication of how well things are going. So if our agent is driving the car, the interpreter can indicate that the car crashed or that the agent reached the destination, so it gives some feedback, and also gives the agent information about the state, using, for example, cameras and things like that. So what we want here to do is to use this information. So the agent is deciding actions, has some effect on the environment, the states change, and there is some feedback on the agent, but we want to adjust the decision the agent is doing, the way it's choosing the action, in order to improve some measure here, which is this reward. So we want the reward to be as high as possible, and we need that interpreter system to be giving the correct rewards and information on the agent about what we want. So basically we can say that if the agent reaches a goal, wins the game, reaches with the car safely to the parking spot or something like that, there is a positive reward. If something goes wrong, there is a negative reward, and we want to change the way the agent decides in order to maximize that reward. So note that there is this feedback between the agent, the environment, and back again for the agent. So the agent has information about how the actions are affecting the environment. But this is not the same situation as in supervised learning, because the reward may not occur every time, and there may be no information on what future actions will result, and things like that. So everything may seem to be going fine until the car crashes against the tree. But in the meantime, there was something wrong that was done back a few seconds ago or a few minutes ago that resulted in that crash. So this is not quite immediately the same as supervised learning, but one thing that we saw with deep neural networks is that we always end up with that same general framework where we give examples and some target values and minimize according to that. So let's first see this notion of a Markov decision process. This Markov property is the property that the probability of some state at some time, given everything that went before, only depends on the previous step. So this may not always occur. For example, if you're taking marbles from a bag of marbles, the probability of each color appearing depends on which marbles came out before, because the proportions will change depending on which marbles come out. But if you are looking at the bag, if you can look inside the bag and can count all the marbles, then the probabilities will not depend on what happened before, because they only depend on the state the bag is in. So the idea here is that if we know the state sufficiently to compute all of this, then we can discard everything that went before. And this we can usually do. For example, if you're teaching the computer to play chess, you can show the chessboard and the position of the pieces, and in that case, it doesn't matter what the previous moves were, because it only matters what the position is now. If you were modeling things differently, for example, registering each move, then the agent would have to compute where the pieces are, looking at the whole history, but that would not be very convenient. So the idea here is that this is a useful property, because we don't need to look at all the history of events.
But shouldn't we look at some of the history? Because it says, was said before, when we look at immediately the last state, what went wrong may have happened like 2 states ago, but not immediately on the state.
Well, there are 2 things here. One is the description of the state and how the state will evolve depending on the actions, which we need to model in a way that we only need the previous state to know the next state. So it's a Markov process. Okay? If we model it like that, we don't need to look at all the history. A different problem is, at the moment the agent does an action, the agent needs to be able to estimate what will happen in the future all the way to the end. If I move my queen here, will I win the game in 10 moves or not, or something like that? And that is a different thing which we'll see to choose the actions. But the first step is that we need to model the system in a way that we only need to look at the state as it is now to work out how things are going to be later on. Okay? So this is one basic idea here, because this is a useful property, not having to look at all the history to understand what will happen next. So a Markov decision process is composed of so this is basically a tuple of these sets. This is the set of states that we have that describe all the possible states that the environment can be in, the set of actions that can be taken, and then the probability for each action of the going from one state to another. So basically we have a table of all the combinations of states for each action. That tells us if we do action 1 in this state, we go with the probability of something to this state, to this other one, and so on. This is possible because we have a Markov process, so we don't need to look at all the previous states, we only need to look at the transition between one state and the next. Then we have the rewards for transitioning from one state to another with some action. Note that this is a general formulation. Sometimes we have rewards assigned to states independently of what the action went there. For example, winning the game doesn't matter if you won the game because you moved the horse or the pawn or something like that. You just won the chess game and you get the reward. But this would be a more general formulation where you can make the reward depend both on the state transition and the action. Then we have the distribution of initial states. Again, in many cases there is only one initial state, but it may be a random state initially. And then this is an important factor here, this gamma for the Markov decision process, which is a discount factor that models this characteristic that it is best to receive the reward earlier than later. So if we're going to win the game, it's better to win the game in 10 moves than in 2 million moves. If we're going to reach the destination, it's better to do so in half an hour instead of 200 years or something like that. So this is basically a factor that says that if we are receiving a reward now, the same reward at times t would be worth gamma raised to the power of t. So if gamma is, say, 90%, receiving the reward one step from now is only 90% of what it is now. 2 steps from now is 90% of 90%, and so on, and it keeps reducing. This way, we are favoring getting the reward in as few steps as possible. And then we have this parameter here, which will be the planning horizon, would be the maximum number of steps that we can consider infinite, or in some situations we can have a limit on the number of steps. So this is what we need to define this Markov decision process, and this is an example here. So this is a classical example of the frozen lake. We have these states. State S here, so state 0 is marked with S, which is always where we start. So in this case, the distribution of the initial states is always this one. All of these F here are frozen, the water is frozen, so our agent can walk there. But these are holes here, the ones marked with H, and when the agent falls there, it's a terminal state. So it ends, it fell into the hole, it cannot leave. And then there is the goal here. This is the one that gives the reward if the agent reaches there. So this is a description of the states, and then we need a description of the actions. There are 4 actions. Try to go north, east, south, or west. But the ice is slippery, so we have, when the agent tries to act in a way, the movement may not be as the agent wants. So actually the rule is that if the agent tries to move in a direction, there is a 30% or 1/3 chance of going into that direction, and 1/3 for each of the side moves, because the agent can sleep on the ice. So if it's in state 0 and tries to go north, there is a 1/3 chance of going north, and then it will stay at state 0 because it cannot leave the lake. There is a snowbank there. The same thing if it tries to go east, but it may end up going west and so fall into state 1. And if it tries to go south, the same thing, and so on. So this is basically the table that tells us for each action what should be the actual outcome and the change with different probabilities in the state of the system. There is one reward if it reaches the goal. The starts at S, and we can use a discount factor here. So basically this gamma for obtaining the reward sooner. This means that if we are here and we are reaching the goal in 1 step, this means that we receive, so if we are at the goal, we receive 1. If we are a few steps away, we receive gamma raised to the number of steps multiplied by that goal. So this means that there is a greater expected reward if we take fewer steps to reach the goal. Okay, so now let's think about how to make the agent move here. And one important difference is between a plan and a policy. So a plan would be a sequence of actions to navigate through the frozen lake here. So this would be a plan. Try to go east, east, then south, 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 and then east. So this is our plan. The problem is that since the ice is slippery, we may end up on different places where we did not want to go. So having a plan may be sufficient if you have a deterministic system, but if there is some randomness, then you may end up outside what you planned and you no longer have a plan. So in this case, you can see that a plan is not enough. What we need is a policy, and the policy is basically the probability of doing, the distribution of probability of acting in each particular state. So in this case, we are considering a deterministic policy, so we're only going to take 1 action in each state, and this would be the scheme of the policy. We don't need policy for terminal states, because when we reach these states, we can no longer act, so there's no need for actions there. But for the other states, we specify which action to take if we reach that state. So we try to go here and then here, but if we are here, we try to go back, and things like that. So this is basically what we need the agent to learn, a policy, so the agent can navigate through the states and always knows what it needs to do. Now, one problem here is that there are many different policies, and we need to figure out which one is the best policy if we want to optimize the reward. So one possibility would be, let's make a greedy policy where we always try to move towards the goal. So if we're here, we try to go this way. If we are here, we try to go this way. If we are here, we try to go this way, and so on. One problem with this one is that there are lots of places where it's risky to try to do this move. For example, here, there is a 1/3 chance of falling into this hole. Here, trying to go south, there are 2/3 chances of falling into a hole and only 1/3 of actually going south. So since the ice is slippery, this may be a very risky policy, and it may be safer to try to do things like this. For example, here I try to go west, because either I go north or I go south or I get stuck in the bank, but I won't fall into that hole. So I'm trying to move away from the hole as the ice is slippery. And the question is it better to try to do this, or is it better to try to be safe and do that policy? So now we need to have a way of evaluating policies and estimating what would be the reward we get. So this would be the state value function. This is something that allows us to get this estimate, which is the expected return from a given state if we follow a specific policy. So the policy is pi, represented here. This v pi s is the expected return from state S following this policy pi. So basically, we are looking at the goal, the reward that we get here in the goal at some specific state. There may be several places where we get rewards, but basically we have to look at this and see what is the expected reward there. Now, this would be, for a given state, the reward we are getting at that state, plus the reward on the next step, assuming we are following this policy, but discounted by gamma, because this comes in the future, is not worth as much, and so on, starting from this state S. So basically, this would be what we need here, but we can convert this into this equation, which is the expected value following the policy pi of getting the reward now, and then the discounted sum of all the rewards all the way to the end once we start from this S here. Because we can do this recursively. So we see what the reward is now, and then discount everything that comes up. So this would be, give us the Bellman equation, which says that for the state S following policy pi, we can sum over all the possible actions taken in state S, given the probabilities by the policy. So remember that in this particular case, we are assuming deterministic policy, so this would only be one action, but for a more general case, the policy can be 90% chance try to go west, 10% try to go north, or something like that. So we consider the different possible actions with different probabilities, and then we consider the probability of passing to each possible state given that action. For example, here, if we try to go west, we may end up with the 2/3 probability in the same state because we hit the snow on these two sides, but 1/3 probability we can go to state 4. So we can consider the probabilities given that we chose this particular action to go to different states, and then we multiply that probability with the reward that we obtain by going from state S to S prime with that particular action. So this is guaranteed. If we get a reward, that's the value there. And then the expected reward from then on following the policy pi, which is basically discounting using gamma and then using the same function v with policy pi from this state S prime on. So we are looking at the different probabilities of actions, the different probabilities of state transitions, and everything that goes in the future is discounted by gamma. So this allows us to evaluate what would be the expected reward discounted by the future for state S following this policy pi. And there is this principle of optimality which says that if we have an optimal policy, then we not only get the best reward for this state, but it's also guaranteed that whatever state we end up next, we also have the best reward if we follow that policy. So this would be the idea. Even if things go wrong and we don't go exactly where we want, if we have the optimal policy, we still get as high a score as possible given the circumstances. And now we also can consider this action value function, which is very similar to the state value function, but it considers what would be the expected reward if we take action A now and then follow policy pi. This is not exactly the same because with the state value function, we assume that we are following policy pi, and so we may take different actions with different probabilities. But in the action value function, we are considering for state S, if we take action A, what would be the expected discount outcome of this? So we only need to consider the probabilities of transitioning state given that we have action A, and then we have the same thing afterwards. Okay. So basically, it's the same thing as this, but we already chose the action, and we can see which action would give us better rewards, for example. An action advantage function can tell us how much better some particular action is relative to some policy. And this would be the difference between the expected reward discounted over time of taking action A in state S and the expected reward discounted over time of starting from state S and simply following the policy. So if it's zero, it means that our policy is giving us the best action, or at least as good as this one here, right? But if this one gives us a higher value than that one, we know that we can do better than what the policy is telling us. So if we have a positive action advantage function, we can see that there's something we can improve in the policy. So this leads us to how we can optimize policies. We can improve a policy by replacing some action the policy recommends, or the probability it recommends, with an alternative that gives an advantage. So if the policy is recommending something different that gives us a lower expected reward here, then we can say, oh, in this case, it's better to take action A than whatever the policy was telling us. And so we can improve the policy in that way. So basically, we want to find a policy that maximizes this. So this would be the ideal policy there, represented by the star, which is the maximum over all the possible policies. So the policy that maximizes these different expected returns for the particular state. This would be what the optimal policy gives us, is the best possible value there. And the same thing for Q, which is the action state value here, which would be maximizing over all the possible policies the expected reward discounted over time. Going for the Bellman equations, this is basically this. We are, in this case, with the state value function, we are maximizing for all the possible actions this future reward, because this is what the policy is determining, which actions we do. And for the state action function, since we are assuming that we are already taking one action in this particular moment, then actually we are looking at probabilities of transitions, the reward we get, and then the discounted, multiplying by this discount factor, the maximum that we can get for all the future decisions we're going to make. Okay, so there is a slight difference here, because this one is just the expected reward given this state and following the policy. We don't specify yet the action, so we're maximizing over all the actions to see which one is better now. But here we already specified the action, and only on the next step will there be an optimization. So the question is, how do we find this? The first question for doing this is, how do we find the state value function? Given a policy, how can we find the values for all the steps? So this is one algorithm that we can follow, is doing this iteratively. We can initialize this matrix here, which tells us this is basically a table that for all the states gives us the expected discounted reward. But we just need to put 0 on terminal states. When we reach the end, there is no future reward. We already reached the end. Other than that, we can initialize arbitrarily. For example, we can put 0 everywhere. And now we're going to apply this policy evaluation equation until it converges. So basically what we have here is that we can update the state value function by using the distribution of probabilities of actions on this state, the probability of the state transition, the reward, and this is given by the game itself, by the rules of the game, so to speak, and then discounted what the previous iteration of our table that gives the values for all the states is telling us for the next state we get in. So intuitively we can think that we start this at random or at 0, And so there is no information coming from here, from these estimates, but there is information coming from the rewards, because the game is actually telling us if we reach that state in that particular way, we get a reward. So as we iterate here, we start propagating that information over the connecting states until we fill the whole table. So we can do this in Python. First thing you need, if you want to play around with these examples, is to install the OpenAI Gym. Just to do this on the environment where you have that you're working with. And then you can use this, the frozen lake. So basically, from the gene you make the frozen lake, and you get from the environment this table of probabilities for the transitions. So this is basically a dictionary of dictionaries where you have the state, the action, and then you have a list of tuples that have the probability, the reward, whether or not you have, probability, the next state, the reward, and a flag indicating where if you reach the terminal state. So basically this is what we can use to experiment with this. You can write your own if you want to create your own game, but this would be a practical first approach. And this would be the algorithm for evaluating a policy. So given a policy pi that we're going to assume that is, in this case, it's deterministic, so it's simply a dictionary where for each state we say what the action will be. And this probabilities structure that tells us the probability of transition and the rewards of taking actions in particular states. We now can start with the state value function x0 for all the different states. And then we are going to loop through all of these possible actions and possible states and possible actions, get the probability of the next state, the reward, and the flag. So for each of these are the elements of the tuple. And now we're going to update our estimate of the state value function, current estimate of the state value function, where we are going to use only the action corresponding to what our policy is telling us for this particular state, and then we're going to look at the reward, and basically this is the information that we're getting from the actual game, the reward. We're going to discount the expected return over the next state here, and this not done is necessary because if we have a terminal state, there is nothing on the future to reward. So all of this term here will be 0 because we cannot keep moving. Okay? So basically we're going to use the reward that comes from the game, our previous estimate of the future discounted value from that state on. We're going to update here, and we're going to repeat this until all the differences between the two iterations of our state function, state value function, are below some threshold that we can set at some small value. So basically we are converging, and then when we are no longer moving significantly, we stop. So this is one way of finding the state value function, and we can now apply this to these policies. So we specify the different policies. For example, our greedy policy has an expected discount return using a 0.99 for gamma of 0.03 here. This one, that is a lot safer, has an expected discount return of 0.41 at the first state. And these are the expected discounted returns for all the states of the different policies. And this way we can immediately see that this one is much better than this one, so it's better to be safe in that case. Now, using this V function, we can compare policies, but if we simply generate policies at random and then try to evaluate them and choose the best one and so on, this will be very inefficient to find the best policy. But what we can do is we can use this Q function, which is the state action value function, that tells us what is the expected discounted return of taking a particular action in this state. And this way we can then optimize the action at this particular state. What we need is the state value function for this. so that we can figure out, if I move this way, that will be the expected return, if I move this way, that will be the expected return, and so on. And so for each state, I can find the optimum action, assuming that I'm going to follow the policy in the future. Of course, then I can change the policy and recompute this, but since I can compute the state value function if I have the policy, and I can find the best action if I have the state value function, I can do this iteratively until I have the best policy for this game. So this would be for the policy improvement. We have the state value function there that we computed before. This gives us the expected discounted return for all the states. We have the probabilities of transitions for each particular state that we are, and the rewards and so on, so we can find this. And now we can do this for all the states, for all the actions. We can check the reward and so on, and we can maximize for them. So basically, what we have here is that we are computing the state action function for each state and for each action. And now we can create a policy by looping through all of these and finding the maximum, the action that maximizes the state action function at each state. So this policy will basically be the acting in a way that maximizes the state action value function for each particular state. Of course, this was computed assuming this state value function that was computed for a previous policy. So this will not immediately give us the best policy because we are trying to choose the best actions, assuming that we do the best action once, but from then on we follow the policy. That is what gives us that state value function. So we need to do this iteratively until we converge. And basically, we start with a random policy, in this case. Now we do the policy evaluation to get the state value function for this policy. Now we create a new policy which consists of taking the best action at each state, assuming that we otherwise follow the original policy. But now this is an improved policy, and if it's different from the previous one, we continue. So if the improved policy is the same as the previous one, we stop because we are no longer changing anything. But if there are differences, we continue until we reach convergence. So now, using this, we can see the different policies. This is the first one. We thought of greedy, trying to move straight into the goal, which is very risky. This is a bit safer, and it gives us a better expected discounted return when we are here at the beginning, but there is actually some room for improvement. For example, trying to go north here is risky because it gives us a 2/3 chance of falling into a hole. It's actually better to try to go into that hole because it gives us a 2/3 chance of moving here. This is not very intuitive, trying to move into a hole, but in this particular case, it improves the odds of avoiding holes. So there are some changes like that the algorithm finds when we try to find the optimal policy. Okay, so to sum up this part, we saw this context and the idea of reinforcement learning. So we have some feedback from the system in these rewards. We have this interpreter that is telling us what the states of the system are and what the rewards are. We also have the agent that has to make decisions, act. But then there are probabilities of different results, the different outcomes of the state, and we need to find a policy, a set of rules for the agent to follow, so to speak, that can be either deterministic or probabilistic for the agent to act. Now, it's important, this is the notion of Markov decision process, and so everything that we saw here depends on this, that the information we are getting from the system at each iteration, so the state that we can observe, does not require us to consider the past history of what happened. It has all the information necessary to decide from then on what we're going to do. Otherwise, if that is not the case, then we cannot simply do this kind of recursion where from each state we consider only the next and then whatever follows next and so forth. Now we saw these Bellman equations and this dynamic programming approach where we can consider this step and then discount whatever comes next in this recursive way. And we saw how to evaluate policies and improve policies. If you want to learn more about reinforcement learning, I strongly recommend this book. This is very easy to understand, lots of examples, and I'm following it a lot here. So the first 3 chapters are about these topics here, but then it moves on to deep reinforcement learning.